Testing. Okay, so let's start. Any question from last lecture or not? Do you guys read? Did you guys read my lecture notes or not? No, not often. So you must at least read once, okay, and then compare with the textbook notes. Okay. Huh? Which part? Okay. Yeah. So if you read my lecture notes, right, if you don't understand, then you come and find me, ask me, okay? Yeah. Okay, I added this slide here. So the mathematics come from a root word from Greek called the mathema, which means that which is learned, what one gets to know. Okay, so mathematics really means study. So if you don't like study, probably you don't like mathematics. Okay, yeah. So it's the desire to learn, desire to study. Okay, there's a drive you to do maths. Otherwise, you really feel very, very tortured or tired when you do maths. Okay. Okay, it's a desire to study, desire to learn. That makes you love maths. Otherwise, you will feel really tired. Okay? Okay. Understand? Seeing, understand 了？解释一下。Okay, almost 啊，Yeah，就是学习的欲望才会让你爱上数学，不然的话你就会很累。OK，OK，Yeah. It's a desire to learn, okay, to study that drives you. Okay, so also I put a slide right here. I put in my lecture notes. I say, when you study about Fourier series, right, just focus on how to compute Fourier series and Fourier transform. That's all. Okay, and if you can do extra things, understand it that add on to your knowledge. But for the exam purpose, you just need to know how to compute Fourier series and Fourier transform. Okay. Yeah. Make sure you know what integral you need to do. Okay. What function you need to use. Okay, to do integral. That's all. Okay, for this chapter. And I also go really quite fast on this chapter. So not deep knowledge need to be no. Okay. I think we should do real calculus now. Okay, when I mean real, it's a real number, real calculus. Okay. So since we are dealing with real calculus, right, we must at least know what is real number. Okay, what is real number? You know what the real number is? Huh? Anyone define real number for you already? Yeah. Huh?
that's not negative numbers in the root.
Okay. Okay. So you are like, you have a complex number in your mind then. Okay. How about the rest? Any idea what's real number? What do you call a real number in your high school? 指数? You? Okay. Yeah, sure. Okay. 指数 is the terminology, and then maybe yours is the definition. Okay. Yeah, let me get my page out. Okay. So let's review some real number knowledge. Okay, so what's a real number? So the real numbers. Oh, okay. Oh, sometimes we call it a real line. So in a moment, I will tell you why is it a line. It is the set of all irrational and rational numbers. Okay, so irrational and rational numbers. So number of nature is discrete, right? So when you learn number, what are the first number you learn? 1. Okay, 1. Then 2, 3, 4, 5, and then so on. So these are called the natural number because they are natural, right? Natural to a human. Okay, and then what's the next thing you do? Okay, what's the next thing you do? The next thing you go is to go to integer. Okay, so you add in 0 and then -1, -2, and so on. So you can notice that these negative numbers, right, if they add to their positive counterpart, you get 0. Okay, it's like you own people money, right? You got -2 money. Okay, you own people money. Okay, so when people do business, then this minus will come out. And then what's next? Rational numbers, right? Right. So next is the rational numbers. What are the rational numbers? These are all the numbers that can be written as fraction. Okay. M over n. Okay, such that n in the integer. Okay, so for example, what? For example, half, right? 3 over 2. Sorry, half is in here. And then 3 over 2. Then maybe 5 over 2, 2.5. Okay. So next is a big leap in human history. Okay. So this is why we call these rational numbers, irrational numbers. Right. So in long time ago, these Greek people think that these are all the numbers used by our nation. Okay. We can think about this number. All the numbers we can think about are these numbers. Rational number. So they are rational. Right. Seng, do you know what's rational? Okay. Right. Huh? No, rational as in a normal English term. No. Rational. Rational is a valid English word. 就是一个英文单词 rational. 啊？对 Who's that? Who's that? What is rational? Yeah. 有听到吗？ Yeah, so, yeah. Okay. So, why are these numbers rational? Okay, this is what you can think of from your mind. Okay. And then, there's one day, So you know Pythagoras? You know Pythagoras? A squared plus b squared equals to c squared. So Pythagoras is a school called Pythagorean school. Okay. So they believe that rational are all the numbers. Okay. But there's one day the guy tell them there's one number is not rational. It's square root 2. And then they kill that guy. And then that guy got killed. Yeah. So have you guys learned square root 2 is irrational? How to prove it? Or not? Yes. Yeah, okay. You use contradiction, right? Okay. So you can prove that square root 2 cannot be written as a fraction. Okay. So how to define these irrational number really? So for example, square root 2 is a number that satisfies x squared equals to 2. Okay. So what you do is you form a sequence from all the number that satisfies a sequence such that an square is less than 2. Okay. And then you make this square root 2 as a limit of this sequence. Okay, this is how we build, how we construct irrational number. Okay, so where is square root 2? 1 point something, right? 1.14. So let me make some space for square root 2. Okay. So for example here. Okay, we add in as a limit square root 2 limit of sequence an. Okay, such that an square less than 2. Okay. So why is it a line? Okay, we can keep filling in this hole. Okay, we can keep filling in this hole. Okay, using rational and irrational. And in the future analysis course, you will prove that every rational, in between two rationals, you will find one irrational numbers. And between two irrational numbers, you can find one rational number. This is called the density of rational and irrational. So they are dense. Okay. And in particular, so they form a line. Okay, they form a line. So in particular, you can fill out the whole line here. Okay. No matter how small epsilon is, you can find a number inside. Okay, so you can fill the whole thing. And so this make this real line become a line. Okay, not that the two line here has no end. Okay, there's no negative infinity. There's also no infinity inside the set. Okay. Okay. This is actually what we call the topology of a real number. Okay, this real line. Can you imagine what happens if I add infinity into this line? What if I add infinity into this line? The line become finite? You mean have a finite length? Okay. Okay, sure. So if you add infinity in, actually this line will form a circle. So it will loop back. Okay. So this is what we call the compactification of real numbers. Okay, you can add this in. Okay, but this you will meet this if you go continue in the pure maths route. You'll see this again. But now you need to know that real numbers are all the irrational and rational numbers. Okay. So what's about calculus then? This is just a line. Okay. So we study, what do we study? So we study functions. Okay, we study functions from R to R. Okay. So what's the function? You still remember what the function is? What do you say? Mm-hmm. Okay. 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 So what's the function? So I give you an input. You can only give me one output. Okay. You cannot give me more than one output. Okay. So the function cannot be one to many. Okay. It can be many to one, one to one. Okay. So it assigns input x in the domain. Okay. And then to output in my codomain. So this is a function. Right? This is function. So for example, what kind of function you have? Can you give some example of function you have seen before? Huh? Fx equal x. Yes, this is a very basic function. What kind of function is this? This is actually a identity function. Okay. This is an identity function. Why we call this an identity function? Because we send every element to itself. We send every element to itself. Okay. Maybe more familiar notation you will use like f0 is equal to 0, f1 equals to 1, f2 equals to 2. Okay. And this is a function from, in particular, this is a function from R. Okay. So sometimes you will see me using this kind of notation. Okay, this is like a hook arrow by denoting what element gets sent to what element. Okay, under the function. Okay, on the map is a normal arrow. On the elements is a hook arrow. Okay, so uh, so geometrically, okay, still we deal with geometry, right? Okay, this deal a lot with geometry. Okay, so we send a real line to a real line. Okay, so one technique we can do is we draw the graph of f. Okay, have anyone defined for you what's the graph of f or not? What's the graph of f? How is the graph of f defined? Okay, from high school, right? What do you do for this picture? You plot two axes, right? One is the domain axis, one is the codomain axis. Okay? So, precisely, what is graph of f? So, graph of f is defined to be a map from R to R squared. Okay, such that you send x to the vector x and fx. Okay, so why is it R squared here? Okay, this is actually what? This is actually the domain plus the codomain. Okay, domain plus codomain. But I haven't introduced what's this notation yet. So I won't do it either now, but you need to know there's a plus in the space. I can add space together. Okay. Okay. For now, what you need to know is graph of a function of f to f, r to r, is a map from r to r squared. So why is it r squared? It's because of this. I can add space together. Okay. And I won't define it now. Okay, but you can keep in your mind first. In future, you will make this. Okay. So, for example, how to realize this? How to realize this in particular? What is the graph of the identity function? So, when x equals to 0, we have 0, 0. When x equals to 1, we have 1, 1. Okay, and then 2, 2. Okay, and then minus 1, minus 1. And then minus 2, minus 2. Okay, and then you can form a straight line. Okay, so maybe this. Okay, yeah. So in particular, what we do here, okay, what are we doing here? You see, we are looking at how real line sitting in R2. Okay, so this function tells us how this real line sit in R2. Okay, so you are like transforming a real line into another line in R2. Okay, so it's like you are transforming your domain here into this line. Okay, okay, so this is what the function is doing. Okay, now. Okay, so you need to know what is real number, what is a function. Okay, so you see this is a straight line, right? So can I sit in like a curved line like this or not? Okay, can I sit in different way? Can the line sit in different way or not? Okay, so this is what we're going to study in chapter 10. This is what we're going to study in chapter 10. So chapter 10 is about parametric equation, polar coordinate. Okay, so first we will start with the subtopic curve defined by parametric equation. Okay, so what should we start? So we start with, let's imagine, okay, imagine there's a particle, okay. Imagine there's a particle moving randomly in R2, okay. So moving randomly in R2. So for example, so you have a particle, okay, and then you move randomly. Okay, so let's draw the axis. Do you think this can be defined? Can be described by a function or not? Why? Or where's the problem? Which point is the problem? Any point is the problem? You mean this part? This part here? Okay. Oh, the circle. This part. This part. Okay. Any other problem you found? Stomach. Where is the stomach? Where's the stomach? I can't see stomach. Here. That one cannot. Okay, why cannot? So this is two of them. Okay. So first one, why cannot? Okay, so using the last time I think we mentioned the test, right? The vertical test, is it? So along this point, okay, you cannot give multiple output. Okay. How about this stomach here? Same. Okay, so this summer actually need to go further, is it? So you can do something. Okay. Okay, so you cannot describe using function from R to R. But if my R is not lying on X, I can do it. So for example, I can split these 3 points into time variable. So I reach these 3 points in different time. Okay, then I can do it. Okay, I cannot say I send one X to multiple points, but I can split these 3 points into different time. Okay, maybe in the first second, I'm at this point. Second, I'm at that point. Third second, I'm at this point. Okay, but we can do this. So what do I mean? So let me define. Plane curve. Okay, this is what we call a plane curve. A curve on a plane. Okay, can be defined, okay, by a pair of parametric equations, okay, such that x equals to ft and then y equals to gt, okay, for t equals to in. So meaning what? My time have a finite interval, okay, and then my x coordinate and y coordinate described by the same variable but different function, okay, but different function, okay, but different function, okay. I will give you an example in a moment. So you will think how we can write this as a pair of parametric equation instead of one function. Okay, you cannot write it as a one function, but you can use parametric equation to describe your curve. Okay, so let's see what I'll give you an example. Don't worry. So remark. Let me put some more notation first. So we will have an initial point. Okay, which we call the point FA and GA. Okay, so where you start, we call it an initial point. Where you end, we call it a terminal point. So initial means start, terminal means stop. Okay. So for example, let's look at one example, right? So let's look at a curve defined by parametric equation. Okay, so what's this parametric equation here? So we have x equals to t squared minus 2t and y equals to t plus 1. Okay, I want you to work out now. Okay, so try take out your pen or your Apple pen. Okay, so try work out some xy coordinate here. Okay, I'll give you the time variable that you need to check. So let's check the time where t equals to -2, -1, 0, and then 1, 2, 3, 4. And then see what's the x coordinate and y coordinate you get. Yeah. Try check for these 1, 2, 3, 4, 5, 6, 7 values here. Okay. Yeah. Try work these 7 coordinate out. Then we will compare. So, written in my notes. No, I mean I just want you to like how to say, just do the calculation. Yeah. Make sure you know how to do the calculation. Yeah. I know it's in my notes. But you need to know how to get the solution. Okay. Yeah, make sure you know how to get the solution. Okay. Actually, I'm not scared for you to get the answer. I just scared that you don't, even you get the answer, you don't know why the answer is true. Okay, that's the most worrying situation. Okay. you can see if you know what to do with this parametric equation. Okay, Anoita. Huh? You finished? Okay. So what's the first pair? Yep. Okay, and then second pair? 3, 0, 0, 1, minus 1, 2, 0, 3, 4, 8, 5. Okay, so let's plot this point again. Let's plot this point. So when t equals to 0 in particular, so what happens when t equals 0? It is at 0, 1. Okay, let's plot the 0, 1 point here. Okay, so this is the point where the time is equal to 0. Okay, how about times equals to minus 1? Okay, minus 1 is 3, 0. So here is t minus 1. T minus 2 is 8 minus 1, somewhere further. Okay, so here is t minus 1. Okay, and then t equals to 1 is minus 1, 2. So you go up. T equals to 2. And then how about t equals to 3? So 3, let me check. So this is t equals to 1, right? So let me move this guy up. Whereas t equals to 2 is 0, 3. So to the top. And t equals to 3, 3, 4. Okay, so go up. And then t equals to 5, go further up. T equals to 5. Okay. So what we can do, of course, you can do more checking on times, right? Okay, but our curve is a continuous, so somehow we can just connect all these dots. Okay, but to be precise, you can fill out more points here. Or in future, we will use the differentiation to check how is this curve, how is this curve. Okay, so this is the curve, and then this is the curve with what? With orientation. Okay, so we go from negative time to positive time. Okay, from the bottom to top. So we'll describe this curve as a parametric equation, but this curve we cannot describe as a function from x from R to R, right? Okay. Yeah. This is not a function. Okay. But we can use two function in times to describe the curve. Okay, this is called a plane curve. Although we cannot write y in terms, we cannot write y in terms of x. Okay, but actually you can check that we can write x in terms of y. Okay, yeah, actually we can write x in terms of y. So actually x is equals to y squared minus x for y plus 3. Okay. What happened? What happened? What happened? Everyone happy or not? Happy with this? You can check that this graph here actually is x equals to y squared minus 4y plus 3. Okay. I think you have seen this before actually. So do you know how to get this equality here? Find one is t and then sub it back. Okay. So if this is true, okay, if this is true, so how do I express y in terms of x actually? Any idea? No? Yeah. I think you need to do completing the square. Yeah. Anyone remember how to do or not? I forgot. But you will write y equals to some fx, okay, some square root thing, and then plus minus 2 part of it. Okay, can you try? So try, write y in terms of x with completing the square. Okay, maybe we all go back and do it. Okay, I will do it. Completing the square. So if you tend to write y equals to some x, then you will split this graph into 2 parts. Okay, how do you split this graph into 2 parts? This 2 plus minus actually referring to cutting this graph into 2. Okay, so the positive part will describe the top part, and then the negative part will describe the bottom part. Yeah, and then how to get the whole picture here? You need to somehow glue these 2 curves together. Okay, in particular, you should glue at this point here. Okay, and this is an advanced course which we call the Riemann surface. Okay, so all the Riemann surface is built up by gluing these different surfaces together. Okay, so we all try and go back and write down this 2 function using completing the square. Okay, and then we can check. You can check with me. Okay, so next. So do you guys all have my answer now? Is it? Maybe close it for a while. Try and work out what's this curve. Okay, I'll let you discuss maybe for 3 to 4 minutes, 5 minutes. Okay, try and figure out what is this curve, and try not to look at my note now. Yeah, what's this curve here? Circle. Wow, so fast. So why is it a circle? So this x and y coordinates satisfy one equality. Okay, what's the equalities here? S squared plus y squared equals to 1. Okay, because cos squared plus sin squared equals to 1 is a triple identity. Okay, so anything that satisfies this equation is a circle. Okay, so this is a very basic, fundamental, important curve in this course. Okay, later we'll keep coming back to this circle, Okay, you must remember cos t squared plus sin squared equals to 1. Okay, so this is a unique circle centered at the origin. Okay, so when you talk about circle, right, 2 things is important. One is the radius, one is the center. Okay, so you need to specify these 2 things to talk about circle. Okay, so you can actually check that this is really a circle on the center at the origin with length 1. Okay. So what is cos t and sin t here? Okay, so for example, if you want to look at this point, okay, so the x here will be cos t, okay, and then the y there, let me use another color, and the y there is the sin t. Okay, in this case, what is the t here? T is actually the angle from the x-axis. Okay, so we count t from the x-axis here. So where's t? T is here. So let me make it bigger. So note that our t from where go from where to where? 0 to 2 pi. Okay, so we start with the positive x-axis. Okay, and then 0, and then go over around and then get 2 pi. Okay, so we loop the circle once. Then we get a whole circle. Okay. So similarly, you can note that this is a function or not? This flat curve. It's not a function, right? Is it a function? No, it's not a function. Okay? But from this equation here, can we express y in terms of x or not? Can. How? Y actually is equal to 1 minus x squared and then square root. But you have two parts, plus and minus. So this is not a function. You need two pieces of function to build out the circle. So where does these pieces get cut? Yes, so actually you cut at x-axis. So the top part is defined by, so let me write. So y1 here, y2 here. y1 is square root 1 minus x squared. y2 is minus square root 1 minus x squared. Okay, and then remember this is what we call the Riemann function. So Riemann surface. So we use a Riemann manifold. So Riemann manifold means you glue different pieces of manifold together. And then you glue at these 2 points here. So if you go deeper in the pure maths, you will see this object again. And more complicated objects. Okay, more complicated objects. You will see. So these are not surface yet. Okay, these are just a line. So in general, we call this a manifold. Okay. How about next? Next. So next, yeah, now I really want you to work it out now. So try and find a pair of parametric equation for the center, for the circle, okay, with different center, okay. Let's say HK with radius up, okay. So all the variable can change. So try and find a formula for this. If I change the center, okay, if I change the radius, how does it affect the parametric equation I have just now? Yeah. Try and think about it. Don't look at my note first. Okay, try and think about it. Try think about it, how to derive it. How you derive this? You can discuss if you want. Okay. What can you try? What can you try? What can you try? How to relate this to our case before? Unit circle at the origin. How does this compare to the example we did? What can you do first? Any idea? Yes. how to relate to the previous example. This is a generalization, right? Okay, we move the circle and then we make it bigger. Okay, so how to relate back to our previous example? The origin, I can translate. Okay, I can translate the whole circle back to the origin. Okay, so for example, I can translate my x by the point h and k, right? So I can translate back my x and translate back my k such that my circle is centered at the origin. Okay. Yeah. So now your job is to find how I describe the x coordinate and the y coordinate here. Okay. So how to describe x coordinate and y coordinate of this triangle? X coordinate is what? So let's say this angle here is called T again. Okay. So what's the x coordinate you should have? Huh? R cos T. Okay. And the vertical one is R sine T. Okay. So your S after translating should be equal to R cos T. And then Y after translating you should get R sine T. Okay. So for T in between 0 until 2 pi, because you just want a full circle. You don't want to go more. Of course, you can add more to T. So this means you will loop this circle few times. Okay, you will more than one times. So in general, what do you get? So you get what x equals to r cos t plus h, and then y equals to r sine t plus k. Okay? For t in between 0 and 2 pi. Okay. And you should also check that this really satisfies a circle equation. You know how to check this plane curve satisfies a circle equation or not? Square what? Okay, so you square x minus h and add with y minus k squared. You should check that you get r squared. Okay. Yeah. So from here, you also can see that these are the center of your circle. Okay, h and k. Yeah. Okay, any question or not? Okay, if no question, maybe I'll leave the other two exercise for you to try. So one exercise is to provide solution. I think you also see the solution. So you need to show that x equals to square root 1 minus t squared, y equals to t, where t is less than equals greater than minus 1, less than 1. And then if I have another parametric equation, okay, actually they are the same thing. Okay, they are the same thing. Actually, we can briefly discuss what is going on here. Okay, let's briefly discuss what is going on here. Okay, yeah. Okay, so let's briefly discuss what is going on here. So I think which one is more familiar to you? A or B? B, okay, because B is a circle. But you need to take note on the interval here. Okay, what's this interval here? Minus pi over 2 to pi over 2. And where is minus pi over 2 to pi over 2? Okay, so let's go back. So here is 0 up to 2 pi is here. So minus pi over 2 meaning you go clockwise. Okay, you go clockwise. Okay, go clockwise from positive x-axis to pi over 2. So it's here, negative pi over 2. 2 pi over 2 is this side actually. So you only get from this to this. So you get the upper hemisphere circle. Okay, upper hemisphere circle. Right. So you get the upper hemicircle, upper semicircle. Okay. So I want to show that A and B are equivalent. I want to show that A and B are equivalent. So meaning A should describe the same curve. Okay, can you see why A describes the same curve or not? See, x equals to square root 1 minus t squared. Remember just now what we did? We take a circle equation, okay? We find y in terms of x. Okay, similarly, you can find x in terms of y. So just now we said that the positive part is referring to the top and the negative part is referring to the bottom. So let's check whether this is true for this. Okay, so says what? So x equals to square root 1 minus t squared, y equals to t. Okay, so these two numbers here also satisfy a circle equation. Okay, with radius 1. Okay, yeah. So the question is this upper semicircle? We can try point, right? If you cannot see the whole picture, what's the first example we do? We test point. Okay, we test point. So in particular here, you also can test the point. So there are two obvious points you should test. One is the two of them are the endpoint, -1 and 1. Okay, if you plug -1 and 1 into this point, what do you get? When t equals to -1, what do you get? 0 and 0. You sure? Huh? 0 or which one? 0. Okay, 0 and then -1. Okay. How about B? Sorry, how about t equals to 1? You also get 0 and 1. Okay. How about the middle point? Let's take t equals 0. Where's t equals 0? 1 and 0. Okay. This is true or not? Hey, where is minus pi over 2? Where is minus pi over 2? Where is minus pi over 2? Pi over 2 is 90 degree or 180. Pi is 180 degree, right? So pi over 2 is 90 degree. Okay, so actually I think we draw the wrong picture, right? So negative pi over 2 should be here. And then pi over 2 should be here. Okay, I think we start with the wrong picture here. So that's why this point like not matches out. Okay, so actually this is the left semicircle. Okay, and then only I think this point will match up. Okay, so the first point you get will be 0 minus 1, which is here. Then 0, 1 is the top here. Okay, and at the middle you have 1, 0. Okay, correct or not? Still wrong. Still wrong. So are they equivalent or not? Maybe they are not equivalent. Cos t is on the right side. Wait lah. So here is 1, 0. So how? Wrong picture. Is it true? True or not? What's wrong? What's wrong? What's wrong? Anything wrong here or not? Just the graph is wrong. Okay, let's check then. What's the middle point here? What's the middle point here? T equals 0. Okay, so when t equals 0, what is x? 1 and y equals to 0. Okay, so what does this mean? So you have the same endpoint, and then you have this. So it's going from here to here. Okay. So meaning what? Meaning this interval here, right? Okay. Doesn't tell you which circle to get. Okay, it just tells you where the direction it should go. Okay, so you should go from negative pi over 2 to pi over 2. Okay? It doesn't tell you which side you have. Okay, it only tell you the direction of the curve. Okay, so to get which side of circle you have, you need to try with the point here. Okay, you need to check the point here. So try and check what is t equals to minus pi over 2 and t equals to pi over 2 also. Okay. Okay. Any question? Any question? Any question? So what I want to say is, so the lesson of the day is lesson the interval of the domain, the time domain, only gives you the orientation of the curve. Okay, only give you the orientation of the curve. Okay, so for a line, there are two orientations you can have. You can go from left to right or right to left. Okay, so here you can go from up to down, down to up, up to down, down to up. Okay, yeah. So to get which circle you have to check some of the points. Okay, so in the end, we go from top left to right. So the final answer is the right semicircle. Okay. So that they're two describe the same thing. Okay. Okay. Any question? About yeah. Okay, so the cyclic example, I will provide solution. You can try out the cyclic the example. Okay. If no question, how about we take a break until 10, 12, 2, 12. Okay.
X 所以有 X 跟 Y，是吗？不是，因为我是把它从一个 one dimension 去到 two dimension，你是写成这样，不是这样，为什么？
因为它只给了一个 y，就它，
这不是这跟另外一个，
因为它只给它，我们就是要看 function from R to R，就是你给我一个 input R，我给你一个 output R，
yes，
然后为什么我们把它画出来？是我们要看它的 graph，所以说我 define 一个东西叫做 graph。
所以它这其实是没有 graph 的 哦，这是有 graph 的
没有 graph of 这个东西活在一个
跳线。
R2 上面，就是不是 graph of 这个东西是一个东西活在它的 domain 加它 codomain 的一个 space 里面，所以这个你这个 case 是 R2咯，所以它的 graph 是活在这个 R2上面。
为什么不要写 R1？
如果我写 R2的话，意思说我给你一个 input R，你给我一个 R2 vector，对不对？
Yes，就是
这样，
不就是 two dimension
所以这是 two dimension 的东西，这样这个就不是我刚才的那个 identity function 了。identity function 是 defined by sending x 去 x。
这样就不能画成一个 graph。
你要画它的 graph， 它的 graph 的定义是什么？刚才 graph 的定义就是你要送它，你要 刚才 graph 的定义是这个，就是graph of f 是定义 as x 跟fx，这个才是 graph of x。graph 是这个东西，这个不是 graph， 这是一个 function。
对，它就不能画成一个，把这个盖住了，它就不能画成一个 graph。
不是讲不能把它画成 graph，如果你要画成 graph，你就要看这个
那不就是这个
啊？
那不就是这个？
不是不一样的东西，这个东西我们叫做 graph，graph 跟它不一样。对，它这个是一个 function， 然后这个是一个 set， 这是一个 set， 这是一 set 东西，然后这个是个 function 是什么？我给你一个东西，output 一个东西，可是这一个是一个 set
我要把它画成，它只是一个
它只是一个 function， 然后我要把它画出来，我叫它 graph。
它就必须是 two dimension 那个东西。
为什么 two dimension 呢？因为我要把它的 domain 跟 codomain 加起来。
哦，不是，还有一个，
嗯
有点像是把它拟成个东西，
哼
一些网上证明啊，
嗯哼。
这样找一下。
Actually, I can straight away use set by because this is a subset of the real number function. Then I can straight away say that if like this thing is the larger superset is true, then the smaller set, the subset of it also is follows the like preserve the properties that I know. I can straight away say that it is decreasing. So
No, my definition of differentiable decreasing is this one. So you need to show this line actually. If the derivative is less than 0, then you need to show that this
I
one.
mean I can
Yeah, okay, okay. I mean, how you use your subset thing on this definition?
because it already mentioned that the Fn is the subset of the Fr to R, right? I can construct a set is like relation.
Relation?
Yeah, I mean like you can make a column and there are the left side is the X and the right side is the Fx. Or the all the I first I define that this function is decreasing. And then because they say that the natural number n to r is a subset of the set A I defined just now, is a subset. So it's like it will preserve because how I say every element in the subset is also in the set A, right? So it's like which automatically proof is decreasing also, right? I mean, no, or I need to write down
What's the definition of decreasing first?
decreasing.
Yeah.
When the x is larger than y, then fx is smaller than f.
But you don't have that condition on differentiable decreasing because I said that if when this function is decreasing, the derivative is less than 0. It's not the definition you have. I only have this definition on the sequence. But this doesn't hold on here. This is what you want. This is what I want you to prove. Yeah. Actually, you need to prove this line. You need to prove this line. This is what I
know. I know how to prove that, but I just want to ask if use the set, the thing can I use that way to prove? That's not
So I ask you, what's the definition of decreasing?
Decreasing is actually the definition. Just now I say that.
No, that is not the definition of decreasing for differentiable function.
I know.
Different? I just said the derivative is less than 0. I didn't compare any 2 points.
The derivative
is
smaller than 0 is supposed to be imply that.
How to imply?
No.
How to imply? That's why I give you the hint.
Okay.
Yeah.
证明的是，如果这个 integral 是，然后里面的一个，OK 啊，我证明这个那个方圈
就是0
啊，就是0。
OK，
那我蛮奇怪的是哦，这个是那个证明啊，
这么你要做这个东西？
因为这个是 integral 在 factor 是，不是讲 linear 的东西。
linear，
我证明如果就是这个咯，
反着正咯，
反正真的，它是2边的，我要正另外一边，从这边开始。
我知道，我说你要正这句话反着正，
反正正，
对不对？啊，
也是可以的。
因为如果你的方向不是0的话，这样你的 x 肯定是。I mean，不，等下要看一下你的方向，你的方向是 positive 还是不 positive？
有2分钟，可以够了。这从这边从负1到1，然后我现在是想要找一个general case 啊，对，我想随便写啊。
对，我看你在做，
我还没有证明。
你要 prove 什么东西先？
我 prove，随便，我要读我
如果这个是0，这个就0。你应该不用证那个你可以直接用linear algebra 应该不会叫你去证可能这东西。
对，
你应该可以直接用那个 result 吧。
但是我是很想写那个，
你想证那个哈？但是这么你的批整到这么乱的，
我还没有写好，我本来是想
这么是这样，你可以给我看一下完整题目。
完整的题目，
完整题目给我看。
完整题目就叫我们证明哦。
我要看一下那个用的 object 是什么，我不知道这么你有这样 specific 的 object。是吗？
啊，就这个。
给我看一下那个题目。OK， 等一下先。好的。Okay, have you tried tutorial question in the textbook or not? Yes or no? Some of you tried, and then you said it's not useful to do my assignment because I don't have those questions. But anyway, those questions is still useful, okay, for you to understand, to practice the theory. Okay, please do it. Okay, so this is what we do in pure maths. So we talk about theory, but we also need to know how to do real examples. Okay, so there are 2 parts of them. Okay, so you need to do those examples and then able to figure out what are you doing. Okay, and actually in your textbook, right, there is also abstract, like abstract question. It's usually at the back, like 50, 60, 70 then. Those are the abstract questions. Okay. And then, those are the kind of questions you see in assignment or exam. Or then you do some practice exam before you have a midterm. Okay. If I don't put it up, please remind me. Okay. Maybe 2 weeks before I will put it up. And then I'll let you try. Okay.
Okay, next. So now we're going to do a calculus on parametric curve. So what does calculus mean? What does calculus mean? Steep curve. Okay. Any more try? Calculus. What's calculus? Calculation. Okay, calculation. Huh? Integral. Okay, integral. Okay. Okay, sure. Okay. So calculus here actually means the infinite decimal study. Okay, infinitesimal study. Infinitesimal study of parametric curves. Okay. So for example, I have a curve, right? I have a plane curve. Okay, I have a plane curve. So how I study this curve? Okay, I zoom in to the part. Okay, I zoom in further. Okay, if I zoom far enough, you could really just see a straight line actually. Okay, so this is the same. Last time I think I mentioned to you already. We are on a spherical Earth. Okay, but when you stand on the Earth, it's as if you are standing on a flat surfaces. Okay, so this is the same as the curve and the bending curve here. Okay, so if you zoom far enough, really it is just a straight line. Okay, it's just a straight line. Okay, I think you are familiar with this. This is called a tangent line. Okay, tangent line or tangent curve. Okay, so if it is a curve, right? If it is a line, right? Okay, how to describe this line? So this line typically can be written as sum y equals to mx plus c, where you describe the gradient of this line at the y-intercept. Yeah, gradient and y-intercept. So let's define the tangents on parametric curve. So what do we do? Okay, so what do we do? So we are playing around with parametric equation, right? So we need to impose some condition here. So suppose that our f and g, okay, are differentiable function. Okay, differentiable function with respect to time or t. Okay, so they are function of t, and then you can differentiate it. So how do we define the tangent line? Okay, so to define the tangent line, what do I need to tell you? I need to tell you the gradient. Okay, so what's the gradient here? Okay, we need to tell you the gradient. Okay, so this gradient is also the dy dx. Okay, at a certain point, for example, let's say we evaluate at x1, y1. Okay, let's call this point x1, y1. Okay, for a moment. Okay, at the point x1, y1. So note that this point is a point on the line. Okay, so meaning you achieve that point using some time. So we call it the time t1, for example. Okay, so achieve at ft1, then gt1. Okay, on my parametric curve or plane curve. Okay, is equals to ft, y equals to gt. Okay, and what else I need? I need one more condition. Okay, I need one more condition is I need to do dy dx, right? Okay, so this means y have to be also differentiable with respect to x. Okay, so they are quite restrictive. There are a lot of things you need to put in so that you can do differentiation. Okay, So you need to differentiate your f. You need to be able to differentiate your g. And then if you write y in terms of x, you need to be able to differentiate it. Okay, otherwise you cannot compute. Okay, you cannot get dy dx. Okay, if you cannot compute. Okay. So what's the point here? So the point here is dy dx is computed as dy dt over dx. Okay. Yeah, I think this is called this is from the chain rule, right? Okay. Can you imagine the chain rule? So, for example, what is this really? So, remind you again, dy dx is not a fraction. Okay, it's an operator d over dx on y. Okay, on y. So, more precisely, actually, x is depend on t in our case, and y is depend on t. Okay, but y is also depend on x. Okay, so actually y is depend on x and t. Okay, here. Y is also a differentiable function of x. So I can write y in terms of x first, but x is in terms of t. So I can compose. Correct? Can you imagine what I say? Can you imagine what I say? Can I imagine? Okay, good. So let's go back to example. So for example, okay, for this curve example here, okay, I can express my y in terms of x, okay, but my x can be expressed in terms of t, okay, so I can go all the way back to t, okay, from y, okay, okay, yeah. Any question on this one so far? Okay, yeah, okay, so we can go all the way back to t. So if you want to differentiate with respect to t, okay, then what's the formula here? So this is just d over dt times y differentiate y x t over ut divided by d over dt xt. This is the chain rule. Okay, so by chain rule. By chain rule. Okay. So since you are dividing, right? Okay, so since you are dividing, so you need to say that the denominator is not 0. Okay, you need to say that the denominator is not 0. Okay. So in particular, what is this line here? Okay, is the tangent line is the line that y minus y1 equals to dy over dx of x. Y equals to x1, y1. Okay, so this is the line. Okay. Okay, so in this case, you see, so I want you to think about one thing. So the impose that y is a differentiable function in x. Like we said just now, not all the plane curve we can write as function, right? In most of the case, it is not a function in x. So how is it differentiable in x then? Okay. So how in that case, is it true that we cannot define tangent line on every point already? You get what I say? So this tangent line have to define with y is a differentiable function of x. Okay. But like what I said, like what we discussed just now, most of the plane curve are not function in x. Okay. What more to say differentiable? So does this mean that we cannot define tangent line on each point already? Yeah, at every point. Sorry? What do you mean by yeah? What about the point at pi over 2? I mean, depend on your time interval, right? Whether your time interval include pi over 2 or not. Okay. Yeah, the point is the plane curve might not pass the vertical test. Then you cannot write down the function y integral of x. Then how you define, for example, this point, the tangent? How about defining the tangent on this point? So what to do? Where do you get the differentiable function? Okay, let's look at one concrete example. Okay, let's look at one concrete example. For example, the circle. Okay, let's look at this circle here. You cannot describe the whole circle as y equal to some number because it doesn't pass the vertical test. But let's look at x equal to 0. Okay, you intersect the circle at 2 points here. But can you draw the tangent line or not? Can you draw a tangent line at these 2 points, north point and south point? What's the tangent line? Just the horizontal line, right? Okay. So how do you draw using this definition? What do you do? Plus minus. So meaning you split the circle into 2 parts. So meaning what? Meaning what you do is, I don't care what happened here. I just zoom in here. And then this is a function in x. And then I can use the definition. I draw the tangent line. If you want to draw the bottom one, how? I just ignore the top part. I go to the bottom, and then I write this part as a function of x. And then I draw the tangent line. Okay. So this is an art of calculus. Infinitesimal study. Okay, you just study locally what happened. Okay, you don't care in the global part yet. Okay, you only care about the locality of this object. Okay. Okay. So you somehow ignore what happened at the other place. Just look at a small region. Okay. And then write this part as the function. Okay, y equals x. And then do the tangent line. Yeah. And then all together you can piece them together. And then at all points you will get the tangent line. Okay. Okay. Does it make sense or not? Make sense, huh? Okay. Okay, good. So if you are happy that we are using chain rule to get the formula, then I won't prove to you. Are you happy or not? Using chain rule? Huh? Happy or not? Using chain rule. If you want to prove, then we can prove together. Prove together. Okay, sure. Yeah, let's prove together how we get this formula here. Okay, proof. Okay, so we need to recall from calculus 1. Okay, so from calculus 1, what's the chain rule? Okay, for composite function. Okay, so what's the chain rule for composite function? FGT. Okay, so if I want to differentiate FGT with respect to t, what do we get? We get differentiate FGT with respect to GT times differentiate GT with respect to T. Okay, so this is the thing you should know. Okay, so how do we apply to our case here? How do you apply to our case? Okay, what are our new F and GT? Okay, what FGT we need to pick? So we are looking at YT, XT, and YXT in our case. Correct or not? Okay, so we have these two parametric equation, and then we from the condition we know that y is a differentiable function in respect to x, so we can write y in terms of x, and then x can be written in terms of t. Okay, so we have this composition. Okay, so applying chain rule to who? Let's apply chain rule to y, x, t. Okay, let's apply chain rule to y, x, t. So in this case here we get differentiate y, x, t with respect to x, t, multiply with differential apply on x, t divided by t. Okay. So how to get our form just now? What do we have? We need to find what? dy over dx. Okay, so dy over dx is here. Okay, so we need to draw the other term to the other side. Okay, note that this is a valid differentiation. This is really multiplication. Okay, so we can throw it to the other side. So we divide it on both sides, where we get d over dxt on yxt equals to d over dt on yxt on d over dt on xt. Okay, so in other words, this is just dy over dx equals to dy over dt and over dx over dt. Okay, so this is the chain rule. Okay, yeah. We're just trying to write it precisely, but it's just really playing around with chain rule. Okay. Any question to this proof here? No? Okay, clear. Okay. Okay. So next, let's look at example. Okay, let's look at example how we gonna compute using the guide. So let's look at one curve. So what's this curve here? So let's look at the curve defined by x equals to 5 cos t and y equals to 4 sine t. Okay, let's look at this curve, where this curve is going from 0 to 3. So how does this picture look like? So it is not quite circle. So something a little bit deviate from circle, maybe something like this. Just a sketch. Okay. So the first thing we do is let's find dy dx t equals to pi over 6. Okay. Find and evaluate. Okay. Find and evaluate. Okay. So where's pi over 6? Pi over 6 is how much? 30 radian in terms of radian. Huh? Sorry? I mean in decimal radian. Because our interval is from 0 to 3, right? So if it is decimal, easier to compare. 0.5 something. So it's quite early here. Okay, actually it's quite early. Pi over 6. Okay, t equals to pi over 6. Quite early. There's a quite early point here. So we want to find this. So what do we need to do? Okay, just now we show that dy ds equal to what? Dy dt over dx dt. Okay, so y is given, x is given, y is differentiable, x is also differentiable. Okay, if you write y in terms of x, is also differentiable. Okay, so we can do this. So dy dt, what do you get? 4 cos t. Okay, dx dt you get 5 sine t, and then you have a minus sign. Okay, good. So this is the dy dt we have. So if you want to just evaluate it, you just substitute your t to be pi over 6. Okay, so if you substitute t goes to power over 6, you will get minus 4 square root 3 over 5. Okay. Are everyone comfortable with substituting t equals to power over 6? Okay or not? Okay. Substitute t equals to power over 6 to evaluate. Seng okay or not? You know what I'm asking? Huh? Substitute, evaluate the gradient at t equals to power over 6. What do? You just substitute the time into your formula. Okay. Everyone else okay or not? Okay. Yeah. If you are not comfortable, please tell. Okay. Okay, good. So next, how about let us up a level. How about find and evaluate? E square y dx square. Okay, at the same point. So I tell you how you compute dy dx. How to compute second derivative then. So let's try what I will say, right? So dx, d square y dx square by right is just differentiate dy over dx. Right? Okay, so what does it equal to? So you see, my dy dx that I found just now is in terms of t. But you want to differentiate with respect to x. So how? So how? You see, did you see the problems here? Dy dx we found just now is in terms of t. Okay, but now we want to differentiate with respect to x. Does it mean that there's no x here and then it's 0? No, right? Okay, because why? X can be expressed in terms of t. So how you go back and forward with x or t? Or how do you deal with these variables? Okay, so okay. I think this is a valid thing to do. So maybe you want to express all the t back to x. Okay. You can try. Okay, let's try half of it. I'm not sure I can finish or not, but let's try half of it. So since x equals to 5 cos t, t will be cos inverse x over 5. Correct? Okay. So if you sub this t back here, okay, then somehow maybe you will get what do you get? You get 4x over 5 on the top. How about then minus 5 sine cos inverse x over t. X over 5. Correct? Yeah. You can do differentiation on this. You try. You can try and do this differentiation. Okay. But one thing you need to check when you do this kind of variable change, also during your integration by substitution. Okay. You can only do this substitution thingy when the function is invertible. Okay, or the function is 1-to-1. Only you can do this. Okay. Otherwise, you cannot simply change. Ivan, maybe you can try this way, see what you get. Okay, and then let me know. But what we do is I want to go back to variable t. Okay, how to go back to variable t? What I want to do is I want to go back to variable t. How to go back to variable t? I tell you how to get dy dx. Correct or not? Can you view this dy dx as a new y or not? Okay, you view this dy dx as a new y. Okay, so you apply the dy dx formula again, what do you get? You differentiate the dy with respect to t over dx dt. Okay, where does x come from? This is exactly the x that you encounter in the operator. Okay, so this part become a new y. Okay. Okay. Question. Ask. Don't believe what I say. Ask. New function of x. What do you mean? Yeah. I mean. You mean? Oh, it's about x or about t. Okay. This new y is about t. Here we computed. This new y is about t. But the previous y is also about t. For sine t. Yeah. Okay. I mean, what I mean by new y, old y here is because in this theorem here, okay, this y here is anything such that it is what? It is differentiable. Okay, such that it is differentiable. And then I can write y in terms of x, which is differentiable. Okay, this also apply to my new y here. So dy dx also satisfy same condition. Yes, differentiable. Correct. Okay. Yes, correct. It's differentiable. Differentiable with respect to x. Yeah. Okay. Yeah. Okay. Okay. Yeah. So can we compute now? Can we compute now? No? So let's write it down. So d over dt of 4 cos t over minus 5 sine t. Okay. And then differentiate x with respect to t. What is our x? X is 5 cos t. Okay. So to compute the top part, you need to use the quotient rule. Okay, you should use the quotient rule. So let's keep the quotient rule. What do we get? I think we get something like minus 4 over 5 minus 1 over sine square t. Okay, you can try and work out the quotient rule. Right? And then d over dt on 5 cos t is just minus 5 sine t. Okay? So altogether you will get minus 4 over 25 sine cube t. Ivan, you can try your method, see if you get the same thing. Yeah, okay. You can try your method and then see, and then send to me. Okay? Okay. Yeah. Any question? Any question? No? Okay, so similarly, you can do the third derivative, fourth derivative, just iterate the process. Okay, just iterate the process. Okay, good. Probably 2. How about let's do one more example and then we'll finish the day. Okay, let's do one more example. Okay, let's look at the flowing curve. So a curve defined by x equals to t squared, y equals to t cubed minus 3t. Okay, I don't mention the time here. Okay, if I don't mention the time, we just take all the t that can be satisfied by these two equations. Okay, so these two equations here, there's no restriction on t. Any t will work. Okay, we can take the whole real line if you like. So for the first part, let's show that C has two tangents. Okay, at the point x0. Okay, and then find the equation. Okay, and find equation. Okay. So two tangent at the point 3, 0. So let's find the tangent. So you want to find tangent lines, right? So what's the ingredient you need for tangent line? For line in general, how do you find a line? How do you describe a line? Sure, computer choice of point, but you need infinitely many points to tell me the line. But actually, you just need two things. Okay, you just need two things. You just need to tell me a dot with a direction. Okay, so what's the direction here? The direction is precisely the gradient of the curve. Okay, gradient of the curve. So, meaning if I want to find a tangent line, I need to compute dy dx at that point. Okay, I need to compute the tangent gradient. Okay, so by formula just now, to get the tangent gradient on parametric curve, we need to compute using the chain rule. Okay, we need to compute the chain rule. So dy dt in this case here is 3t squared minus 3 over 2t. Okay. Okay. Are you surprised? Hey, why at a single point you have two tangents? Are you surprised or not? Seng, surprised or not? Or you sleepy now? Are you surprised? Why at a single point you have two tangents? Why? Usually one point only have one tangent, right? So why one point and two tangent here? What is going on here? What is going on here? Right? One to many function. Yeah, one to many function. Okay. So it's not really a function. It's a plane curve here. Okay. So this one point here actually is achieved by different time. Okay. So let's check at this point here, how many times it comes back to this point. So at x0. So what are the t's? Okay, what are the t's? Okay. So we said when x equals 0, y equals to 0. Okay, let's find the t. So meaning when x equals 0, 3 equals to t squared. And then 0 equals to t cubed minus 3t. Okay, to be on this 2 point here, the solution from the two equation must match up. Okay, so from the first part, how many t you have? T equals to square root plus minus square root 3. Okay, how about the third part? Actually have how many roots? 3 roots. Okay. Yes. 0 and plus minus square root 3. Okay. So in this case here means what? It means that only at t plus minus square root 3 we will reach the point 3, 0. Okay. Okay. So you come back to the same point twice. Possible or not, Seng? Possible. Okay. Okay, good. So hence when t equals to plus minus square root 3, okay, we have our point on 3, 0. Okay. So we can compute my dy dx now. Okay, we can compute my dy dx now. So you can see that why our dy dx is in terms of t. Okay, because on the same point you can come back at different times. Okay, and the different times you come back, you will get different gradient. Correct or not? Okay, it's like you come back to my class in a week, but you feel different. You come back to the same class, but you feel different. Correct or not? Okay. Okay, so when t equals to square root 3, okay, so what is my dy dx here? So I need to sub it back to my formula. 3t squared minus 3 over 2t. So 3 square root 3 to the square minus 3 over 2 square root 3. Okay, similarly, you can do it for minus square root 3. Okay. And then what do you get for two of them? Do you get different answer or not? Try and compute. Do you get different answer? When t equals to square root 3, what do you get? What do you get? You get square root 3. Okay. But when t equals minus square root 3, you get minus square root 3. Okay, so one, you should think of it is like going upward, and the other one is going downward. Okay, so one of them, the gradient is square root 3, and then the other one is minus square root 3. Okay, and try and build the line. Okay, try and build the line. So let's finish building this line, and we'll continue next time. So how to build the line? So at t equals to square root 3, what have you intersect? So you have intersect the point 3, 0. Okay, so what's the tangent line formula here? So y minus y1, t is at square root 3, and then x minus x1. Okay, so this line equation here precisely tells you what? You need a point plus a direction. That's all. Then I will know the whole line. Okay, because you have a line. This line can appear everywhere. But once you specify a point on this line, then this is the only line that contains this point. Okay or not? So you have a lot of equivalent line. Okay, but if you specify one point on that line, then this line is fixed. Okay, this is the line you're talking about. Okay, so in particular, my point that I fix is 0, 3, 0. Okay, and then at m equals to gradient at t equals to square root 3 is just square root 3. Okay, so I would say that the tangent line passing through the point 3, 0 is the line y equals to square root 3 times x minus 3. Okay, so this is the tangent line. So similarly, you can work out when t equals to minus square root 3. Okay, but they pass through the same point. Only difference is the gradient. Okay, so it's the gradient. Okay. Okay. So we will continue this example next time. Okay. Yeah, so if you have any problem, in particular your project one, if you have any idea, please talk to me. You can message me, see me. Okay, so see you next week.